Very good. The camera is set. So let's get started. So we continue with the light race.
Okay. Good morning, everyone. So
Maybe music is not better.
good evening. Yeah. So today we'll discuss a bit more about the Hamiltonian I introduced last time and its solution. So let me recall the operators and the Hamiltonian. So the idea was to look at operators on a like array. So it would be, say, this one would be O. It's a function of 3 null coordinates. Well, the one I will focus on today will be 3, but in general, we can have L of them. And they're separated by Wilson lines. And we're going to be thinking that these are fundamental Wilson lines, and they have to be connected in the trace to make something gauge invariant. So these are a function of 3 points. We describe how these operators arise in a situation like deep elastic scattering, Parton distribution function, hard scattering, distribution amplitude, corneal limit of amplitude, a few contexts. And so today we'll just study the operators for themselves. And then, of course, first, per Yang-Mills, this would be a product of, so trace of Z of x1 plus dot. So it's a trace of this complex scalar field. It's the simplest case we can study. And the Hamiltonian acting on this operator has the effect of taking in turn each of these points and sliding it towards the other. Okay? So it's written explicitly as, well, H12. You can write it, this is a sum of pairwise interaction, where one field shifts towards its neighbor. So I can write it as like this, where, and this is at leading order in the coupling, and this H12 is 2 times integrability coupling times integral 0 to 1 d alpha over alpha times basically twice the operator minus the operator with x1 prime minus the operator with x2 prime, where x1 prime is x1 plus alpha x2 minus x1. Okay? So it's moving toward x2. So that's the form of this Hamiltonian. And we would like to diagonalize it. So we'll do it in 2 ways today. First, we'll do a sort of brute force approach, trying to make ansatz for what function of x we can have. And second, we'll use integrability, actually using, as described in the paper by Pedro and friends last year, with Simon Duffin and Alexander was here. So before we do the direct solution, it's going to be useful to think a bit about the symmetries in general and what kind of operator we're interested, what kind of matrix element makes sense. Because, even if you think of this as a kind of quantum mechanics problem, it's function of 3 variables are annoying. I don't want to make an ansatz for a function of 3 variables. So we're going to use some symmetries to make this simplify our life. So the first case I want to describe is the case where you have what correspond to local operators. The claim is that local primary, expectation values which correspond to local primary, are related to translation invariant polynomials of these things. Okay? So if you want to just study the problem of local operators, we saw last time how these, how we can reduce those to local operators, then we really just have to reduce to compute these work with polynomials. So the explanation is the following. So we're going to think about the matrix element of O in some state. And in general, we could consider a matrix element of O at this x plus in times some local primary inserted at some point y. Okay? And this is the one loop Hamiltonian. So in order to, we're just going to calculate this in the free theory. In the free theory, we need something, and this point, I'm going to draw space-time here, at least Penrose diagram of Minkowski space. And you should imagine that the xi's are on this null ray. They're all null separated from each other. And I'm inserting this point y at some random place. It should not be on this null ray, so that the two-point function non-zero. And then the basic propagator is z of x plus z bar at y. And that is some function that looks like 1 over y minus x plus, sorry, y plus minus x plus y perp square, maybe with a minus here, with some I epsilon. And probably the other minus epsilon, but okay, plus minus, okay. Okay, so it looks like this, and let's look a bit complicated. So you see that in general, you get a complicated function of x. That's not a polynomial at all. The way we're going to get something simpler is that the claim is that, well, the dynamics of this operator doesn't really depend on where we insert the point y. So it's useful to insert it, to take it to infinity. So if you, this point here is called infinity, space like infinity. If you take the point y to infinity, things simplify a lot. And we can, okay, we're going to neglect this y perp square. And the simple way to approach infinity here, this coordinate, is just to take y plus goes to 1 over w, where w would go to 0. Okay. And when you take an operator to infinity, you're supposed to multiply by power of w to cancel some overall divergence. So this two-point function becomes simply 1 over some, well, overall y minus times 1 minus w x plus. And we take w to 0. So you see that if you take 0 times z to the x plus times this operator z bar at w go to 0, and you could take derivative here, you would get the nth derivative of 1 over 1 minus wx plus, which is proportional to a polynomial in x. So if when you insert derivative of the field at infinity, it gives you a polynomial wave function at finite place. And if the thing you insert at infinity is translation invariant, then this is a conformal primary. The conformal generator at infinity is really a translation, so you get a translation invariant state. Okay. So then you can try to analyze these states with the polynomials. Okay. That's the first thing we can do. We will do this numerically, so this is relatively straightforward. So if you say that you have a polynomial of degree j, then you have to enumerate all of this translation invariant polynomial. You'll also impose that they are cyclically symmetric. It's actually a pain in the neck to enumerate cyclically symmetric polynomials. But you can do it on the computer, and if you're smart, you can probably find an analytic solution. But and then you can diagonalize the Hamiltonian on that, acting on this subspace. And this Hamiltonian has the property that when you act on the polynomial, it spits you out a polynomial. So that's great. Let's do it just for a simple example.
Sorry, Simon, can I ask a question? So this polynomial that you just discussed is you're taking a particular choice of this xi's, right? And you're evaluating it in the presence of some primary.
These xi's are arbitrary on a likelihood.
Yeah, sure. You're making some choice. So what does this calculation have to do with the Hamiltonian?
Yeah, so
like the polynomial that you're going to get from here depends on what primary A you pick, and so I'm just a bit confused.
So yeah, it depends on primary A. Yes. So the point is that the twist of this operator has to be will only be this correlator will only be non-zero if the twist of this operator matched with the twist of A. The scaling dimension have to match.
But for no values of xi, this operator is going to have a definite twist. You need to take some linear combinations of these operators as different values of xi.
Okay. So what I explain is that any operator any local operator you insert at infinity will give you a polynomial wave function. If you happen to take a primary, then it will give you a specific polynomial. That will be an eigenvalue of the Hamiltonian. Because there has to be an eigenvalue of twist. The Hamiltonian, remember, is the twist, right?
Okay.
So if you put an eigenvalue of twist in infinity, you will automatically get an eigenvalue of twist defined by this operator.
Yeah, but in this language, are you trying to find A's? Expressions for
We don't
A?
care about A's.
Yeah,
We
but
characterize the A's by their matrix element, which are these polynomials.
Yeah, I just thought you wanted to renormalize the O's, right? And understand how diagonalize the action of H on O's. But here, the wave functions that you're talking about, they're going to depend on A. So if you find some polynomial, that polynomial would correspond to some particular A and describe A.
Correct.
Not a linear combination of different O's.
Correct. So the different eigenvalues of this will correspond to different A's. And you can actually go back. You can reconstruct what A's was in terms of derivative of the field.
Yeah. I
using
understand
this
that,
map.
but I just thought your point was to try to diagonalize it on O's, and not on A's.
Yeah. So we don't care. The A is passive in this equation. So we're just acting H on O is equal to some integral of O at x prime. That's the equation we study. The A is completely passive in this equation.
Suppose you find the wave function.
Yeah.
Then, as you described here, the wave function corresponds to some A. So you learn something about A, and I just don't understand what this wave function does about O.
When you find all the eigenfunctions of A, you learn about all the A's.
Sure. Okay.
The problem of finding all the eigenfunctions of H has nothing to do with A.
Yeah, I just thought that you would multiply O by some wave function, integrate, and then try to find.
No. This is not what we do.
H.
We just take the expectation value of O. It's more simple. It's much simpler like this. If you do the other way around, you could say that the local operator O is the integral of O against some wave function, which the local operator happens to be a bunch of delta function. And then you have to work out what H does in a bunch of delta functions. And this you can do, and this is pretty much the approach that was taken in this traditional approach of writing the Hamiltonian of the what was the name? Sorry, but yeah, in early 2000s, we have when you map the Hamiltonian to a spin chain, you try to write wave function in terms of derivative. That's correct. But instead of taking the operator, you can also look at its matrix element, and it gives you the same. And this will be easier to generalize to non-polynomial states. Okay.
But if you start from Hamiltonian, right? So you're saying, okay, it commutes with translation, right? So in principle, there's quantum number momentum, right?
Yeah, absolutely. So we'll describe momentarily what we can diagonalize. Yeah. So we can definitely restrict to translation invariant polynomial.
Yeah, you can just choose to restrict to that. But then, what is the relation? What's the meaning of this other eigenfunctions? Which
the one that are not translation invariant. But if they're polynomial, they will be descendant. If not, it's more complicated. Yeah.
So in principle, there's continuous parameter, right, in the spectrum.
Yeah, I'll come to that in a second. Yeah. So let's do the simplest example. So if you have a length 2 operator, then the polynomial are x2 minus x1 to the j. And j should be even, so that this is cyclically invariant. And when you act with the Hamiltonian on that, you get, actually, yeah, this multiplies a lot. All the terms look the same, so you get 8 g square, integral 0 to 1, d alpha over alpha. This term was itself. And when you make the operator shorter by this motion, you multiply this difference, x2 minus x1, by 1 minus alpha to the j. Times original O without translation. And when you evaluate this integral, it gives you 8 g squared times the harmonic sum of j, okay, which is the known one-loop eigenvalue for this SL2R sector. So we're working in a convention where the case that is protected, so j equals 0 is the trace of z squared, is the protected guy. So you see that this Hamiltonian is equal to 0. Right. This is the operator that is in the multiplet of the stressed tensor, so it does not require any quantum correction. So simple check of this formula. Yeah, so that's the sort of states we study. Yeah.
Cyclic invariant. So I mean, obviously it's a symmetry of Hamiltonian, but why do you need to impose it? Because it's not that obvious that that's
yeah.
like
So
for local operators.
So we're going to classify the when we go to non-integer spin, we'll have to think harder about this. Yeah. So before we go to integer spin, let's think a bit about the symmetries. Okay. So the symmetries of this operator, well, we can study those directly with Hamiltonian, but I think it's better to think of those as arising from the full and conformal symmetry of n equals 4. So there's a subgroup of SO4, 2 of the full conformal symmetry of space-time that preserve the x plus null line. So x equals 0, x minus equals 0 line. Okay. So the symmetries will originate from that subgroup of the bigger conformal group. And this includes basically the following generator. So of course, dilation, just rescale the line. You have the boost in the plus minus direction. We have all of the transverse direction. So here it will be SO2 perp, general D minus 2. You can also have translation of the x plus direction. Let me make the plus clear. You also have some funny Lorentz transformation that take a plus that boosts in a mix of boost and rotation. And in the end, you have all the conformal generator. They all leave the line invariant. It's quite a lot. Most of these will not really be interesting. Only 3 of these things act non-trivially on the points on the line, so they actually move you around on the line. And they form a SL2R subalgebra. So basically you have P plus, K plus, and when you take the commutator of P plus and K plus, you get something that is a combination of dilation and boost. Okay. So these guys form a SL2R algebra, meaning basically that, so this guy here is called a conformal spin. Its eigenvalues are basically delta plus j. It's convenient to take delta over g over 2 and call it h. Now they form a SL2 algebra, means basically that this h comma p plus is p plus, and h comma k is minus k. So h is the thing that describes essentially the spin of the operator. And you see that p and k act as raising and lowering operators. Another symmetry that's important, that's interesting, is the one we're actually trying to find, is the Hamiltonian. There's a twist which commutes with this algebra, which is d minus lambda plus minus. So it has eigenvalue delta minus j. And essentially the goal of this is to find, we would like to find the spectrum as a function tau of h. Okay. So this h, well, this h more abstractly represents a Casimir of a SL2R representation, and all of the states in this representation have the same value of h. And for each representation, there's a particular value of twist that we find from this Hamiltonian. This SL2R group, the way it acts on the points on the line, it acts by a Mobius transformation. it acts by xi, goes to basically a xi plus b over c xi plus d, where the determinant of a, b, c, d equal to 1. So conformal transformation acts by this reparameterization of this light ray. Maybe an important comment to make, if you're not familiar with so much with Minkowski space. So one thing that happens is if you start with a light ray operator, say that looks like this, it fits inside a Poincaré patch in the usual space-time. When you apply this transformation, it can happen that, well, if d over c is actually lined up with x, you can send a point to infinity. And if you go further, the coordinate will become, instead of going to plus infinity, it will go to minus infinity. So some transformation could send this operator, for example, to something like this, which is not how you should think about this conformal transformation, because this is really like the future, and this is the past. And we don't live in the Pac-Man world where the future is the past. So what you should really think about is about being on a cylinder. So the group that really acts on this operator is a cover of this Mobius transformation, where if you exit the Poincaré patch, you just keep sliding past. But here you should imagine this is a cylinder. So this is R cross S3. The usual space-time is a set of points. So if you fix a point infinity here, the set of points that are space-like from X is, trying to draw a cylinder, and if it were in 1 + 1 dimension, to be literally a periodic identification. In general, this is, you have to try to visualize a cylinder here. But yeah, Poincaré patch is this region. And yeah, the conformal transformation, just slide this thing around and rescale it in a way that this symmetry is preserved. Okay. So what can we can use these symmetries to simplify our life a little bit. So
sorry, very basic question. So why is it? Do the case preserve the line? You said all case.
Yeah. So really? K look something like K mu is something like x square. Let me put d mu here. S square d mu minus 2x mu x dot del. Okay. So x square is 0 on a line, so you don't need to worry about this term. And you see that no matter what coordinate you put here, this will only rescale you effectively on the line, but by an amount which can depend on your coordinate x plus. So what these operators do, maybe it's a good question. Maybe let me describe a little bit more what these other guys do. So what these other guys do is effectively, if you have an object with indices, transverse indices, this can take a transverse indice index and take it into a plus index, or vice versa. So this can mix perp or minus and plus indices. So if you have an operator with spin, it can mix these things a little bit. In general, this setting k equals 0 tells you that your operator is not simply like a simple perpendicular translation of some other operator. Okay? So these will not play a role today. They all act trivially on these operators we're talking about. Okay? But if you're interested in studying operators with gluons and field strength, with indices and so on, then in general these things will become interesting. Okay? So they act on the indices of the field. Yeah, orthogonal derivative sort of. Yeah. Other questions? So the way you should think about this twist is that it's a function of the full SL2R multiplet, and all the states in the SL2R multiplet have the same twist. Okay? In order to compute, we should find the simplest and most convenient state. So there are basically two natural options. one is very natural, is to take states that are killed by p plus equals 0. Yeah. If you have a state with p plus equals 0, then in addition, so that's a translation invariant state. So there's going to be, that will make that O is translation invariant. In addition, in general, we cannot diagonalize P and H, and this conformist and this dilation simultaneously. However, when P is equal to 0, yeah, normally you cannot diagonalize both these things simultaneously because they don't commute. But when this is 0, you can actually diagonalize both. And that's very convenient because we've diagonalized two things. So yeah, basically, let me call this yeah, d plus lambda equals some number. Put it h. Yeah. So this gives you translation invariant wave functions that are homogeneous of some degree. And h is related to j in some way. So basically, we're going to be studying expectation value of x plus, xi plus, that are translation invariant and homogeneous of degree j. Okay. So effectively, we're going to be looking at averages that go like, okay, now I'm going to anticipate the question that Kolya already asked. And I will not answer yet, so but let me just, the answer is coming. So suppose that x1 is less than x2 is less than x3. Then the wave function, you can write it basically as x3 minus x1 to the j times some wave function of a homogeneous ratio, which is only 1 at 3 point. So it'll be something like x2 minus x1 over x3 minus x1 time. Let's call this thing z. Okay. So you see that if you have 3 points, you just have effectively the information is a wave. All the information now is in the wave function of two variables, where z is between 0 and 1. Okay. However, what you really have is 3 factorial of these wave functions, because you have to consider all the possible different orderings, and in principle there are different operators. So in principle you have many wave functions like this, but you have many functions of one variable between 0 and 1. That's how we can characterize the state. Okay. So any state with non-polynomial j can be characterized by such function. That's the first option. Another option which you can do is you can diagonalize to p not equal to 0. So you look at momentum eigenstates in this object. It's still true that things are just function of one variable. So for example, when for length 2, you could have a wave function in this eigenstate will take the form of something like IP x1 plus x2 over 2. You can soak the momentum like this, and then you have a function of the difference. And the function of the difference turned out to be some like Bessel function, j plus half of p x2 minus x1 over 2 divided by square root x2 minus x1 absolute value. So you could make a wave function like just like this. You see it's a bit harder, but in general what fixes this object is that you have a Casimir equation that you cannot diagonalize the second thing, but you can still have use the Casimir equation to reduce you to a function of one variable. Okay. formally, you can go from the state 1 which diagonalize p plus equals 0 to the other states which diagonalize p plus not equal to 0 by acting with k plus repeatedly. So roughly speaking, if you take a function, I work it out schematically. Don't take this equation for cache, but you have some formula like this. Roughly speaking, J, and so if you take a 1f1 of this operator k plus, acting on this translation invariant state, will give you this thing and its generalization to higher points. So formally, you can go from one problem to the other. And the spectrum does not depend on which representative you take because of the SL2R symmetry. And for the purpose of numerics, we'll just stick to this first option. Okay? But in principle, the same calculation tells us something about momentum eigenstates. In terms of physics, these are useful in different situations. So we saw last time this p plus equals 0 operator. They have the property that of course, they annihilate the vacuum. So the operator option A, option 1, give operators. So if you take an operator and you project it to 0 momentum by integrating over translation, it's like you're forcing its Lacan energy to vanish. But because Lacan energy can only be non-negative, that forces the state to be the vacuum. So give operators that annihilate the vacuum. So it's okay because you can take expectation value, say, in the proton state, and it will give you something non-zero. But in the vacuum, they give 0. On the other hand, option 2 is needed to give you something like distribution amplitude. So if you start with a vacuum and want to find the probability that your operator creates a hadron, a proton, or whatever state, or whatever other local operator you have, this matrix element will only be 0 if you take this option 2. But they're controlled by the same spectral problem, so use this fact for convenience. Yeah.
Were these options 1 and 2 different choices of A's?
There are different choices of eigenvalue of p plus, whether you choose it to be 0 or not 0. And indeed, in order to get the state, so the state p plus equals 0 is naturally obtained by inserting a primary at infinity. The states that diagonalize p plus non-zero instead are integrated by doing a Fourier transform at scribe plus. So you have to do a Fourier transform over all these times in order to diagonalize, because p plus is a translation at infinity. Right. Transform it, yeah.
Okay, thanks.
Yeah, when you insert, you can do various things. Here we're inserting the operator in the bulk, and we're inserting the thing that creates the state at infinity. You could imagine doing other things where you insert the state at the origin and insert these likely operators at infinity. This gives the sort of detectors that we talk about. And just for context, this sort of expectation value at infinity, this gives you something that's like quantum numbers of a conformal primary at infinity if you have this translation invariant. These are the things we studied with Peter and friend that we call detector operator, like the energy flow. It doesn't change the momentum of state, just measure the energy. And these things here, they are states which actually create particles at infinity. These are more the things that the celestial holography people want to study scattering amplitudes, where you just have an amplitude and not an expectation value. Yeah. So am I doing on time? Great. So let me show numerical solution. Okay, maybe just say a few quick words for the actual numerical strategy that I took. Maybe, oh yeah, I will have to. Yes.
Will it become a light ray in a different direction then?
Yes, yeah, let me discuss this. So there's some natural structure you can imagine. When you have two such light ray operators, you can imagine various pairings between them. Let me say a brief word about pairings, because that's also important for the numerical algorithm. So there's different natural pairing. One of them is to take between this p equals 0 state. One natural pairing is you can take a state that's going in the plus direction. That's these operators. And then you can pair it with a state that's going in the other direction. So that's basically an expectation value of O of x plus and some O of x minus. Okay. And you have to put the transverse separation such that this is non-zero. This is one natural pairing. This is a pairing that also is natural, gives you somehow the scattering amplitude is high energy limit. I heard that it's actually been calculated in terms of this wave function. It's very not, you have to do a calculation and compute a bunch of integrals to find out what it gives in terms of this wave function, but there's some known formula according to Alexander. I have not used this pairing. You can imagine another pairing, but which makes sense for the operator with p not equal to 0, which don't annihilate the vacuum. And this, you can basically just take two things like this in the same direction. So one would create some kind of hadrons, and the other will annihilate it. This pairing here, so if you take an integral of, this pairing would give something like product from 1 equal I to L of 1 minus x plus I minus y plus I plus I epsilon. Give a product like this. So again, if you integrate the operator against some wave function and want to compute the product, we have a bunch of our integrals to do. One thing that I should mention is that they have different property. This is not manifestly positive definite. So it's unclear whether this pairing defines a Hilbert space or not. But yeah, exactly. This pairing, both of these pairing commute with Hamiltonian because they make sense the full theory at finite coupling. So both of these pairings commute with Hamiltonian, but yeah, it's not manifestly positive, so it's not clear whether you can really think of this Hamiltonian as a remission operator.
Why is it commute?
So if you you have to use the full symmetry of the SO4, 2 of the original theory. And the point is that this operator that have p plus equal to 0, they transform under conformal symmetry like an operator that is a primary inserted at this point. So this 2-point function will transform like under conformal symmetry like a 2-point function of two primaries at different points. And the form of that is protected. So this 2-point function has to give you a number that does not depend on the coupling. And if you diagonalize two different eigenvalues, different h, different tau, you will get 0. It's orthogonal. Yeah, the conformal symmetry answer the 2-point function is 0 between operators with different quantum numbers, is the short answer. This pairing here is the one that was used by Koshimsky, Manashov, and Derkashov and friends. This one here is positive on, so when you Fourier transform with respect to frequency, this is like a projector. When you integrate against a wave function, this is like projecting you on the positive frequency state and positive frequency sector. So this is positive on positive frequency wave function, but 0 on a negative frequency component. So it's kind of a projector on positive frequency parts. That makes sense because acting on a vacuum, the guy in the past have to create particles. So all of these three operators have to have positive frequencies to create particles. And this pairing is proportional to a projector on positive energies. We're not going to use this pairing. Actually, to do the calculation, I do not use any pairing. So the way I will present of calculating this eigenfunction, this eigenvalue of this Hamiltonian, is very simple. Is I will assume that we're interested in reasonable states where this function psi is regular. Okay. So the algorithm. So assume psi is regular, and we're just going to make an ansatz over n, Cn, and it's best to do a Taylor expansion around half. So we'll just do a polynomial ansatz like this, and this will go up to n max. When you act, when you act with the Hamiltonian on a state on this sort of wave function of this one variable z, you get something that takes you outside of the space. So we make a matrix.
Sorry, before you discuss about the pairings, isn't it true that if I have two null lines that don't intersect, that they can always be mapped one to the other? Any configuration of two null lines that don't intersect, I thought was conformal equivalent.
Yeah, these two configurations are conformally equivalent to each other. That's why these operators can be labeled in the same way.
No, I meant the top and bottom pictures. Can't I relate two null lines that are perpendicular in quotation marks to two that are parallel? Because
I think parallel is singular because at infinity let me see. Let me think.
I thought the two were related by a conformal transformation. These two situations.
Yeah, well, this is not the fact that p plus is not 0 means that this thing does not transform as a conformal primary.
Not about p plus, I don't know, but about the picture, is it true or not that the two pictures are related by a conformal transformation?
They don't intersect in infinity, but as drawn, the initial points in the lower picture are null separated, and in the upper picture,
these points are null from each other, so they cannot map singular to non-singular. So here the points are null. So this thing would be very singular if I didn't put. If I were looking at primaries. I get something non-zero by looking at non-primaries. But both this inner product commute with the SL2R symmetry of these null lines. Yeah. So for numerics, we just do this polynomial ansatz. And so that's a relatively simple thing you do. And the idea is you want to take n max to be large and hope that the solutions converge. Then, when you take h of psi, it turned out that h acting on z to the n is something you can calculate analytically for any n, according to Hamiltonian we had written before. But then what we do is I make a matrix by integrating this against integral dz of zm, h to the m. So that gives some h of z1 minus n. That gives some matrix HMN. So you can define a matrix n max times n max of the matrix elements of this. However, you don't want to diagonalize this. You want to say that this is equal to an eigenvalues, small h, times integral of zm times z minus half to the n, which is just, let's call this some matrix CMN. Okay? So essentially, we have to find the eigenvalue of C inverse H. Okay? So that's what we do in the computer. If I had been using a orthogonal inner product, this C would have been, and I use a basis of orthogonal wave polynomials, this C would be 1, and I would just directly be diagonalizing these elements. Yeah, I don't care about that. I just diagonalize, I just project just do this random projection and project onto bases. So it's really the simplest thing you could imagine doing, and it saves some work because then I don't have to calculate this inner product.
Simon, so these operators we are diagonalizing, they are some integrals of some other wave function against the trace, right?
Yeah. Now the beauty is that now I just have a function of psi. I don't have to do any integrals.
Yeah, I kind of missed this point. Can you relate this psi to the standard wave function, which has a different homogeneity and so on?
Mm-hmm. Yeah, but then you will have to do a bunch of integrals. This is a way of organizing calculation, so the only integral you have to do is the integral of the alpha in the Hamiltonian.
I think I missed the point of how isn't this correlator you're defining here to compute this wave function dependent on the state?
This is the average in any state. There's some state psi in any state, yeah. So I'm defining, here's the important point. I'm defining a state by the expectation value of an operator, not by the operator which creates a state. It's conceptually equivalent by inverting the two-point function, but this is this is simpler for calculation, at least for some purposes. Okay, so I'm defining the operator by its expectation value, not by what it creates it.
Aren't you then just computing the spectrum of local operators?
No. No. When you go above, when you take this expectation value can be in any state, and I could be computing in particular expectation value in states that look like this. And there, it's just that I'm not explaining, I'm not calculating how this expectation value is related to exactly the wave function I integrate for the other guy. I just study this expectation value intrinsically. Yeah? And the possible expectation values will tell me the possible, are dual to the possible things I could insert the other side. Yeah, thanks for this question.
So you're not inserting local operators at infinity anymore?
No, not anymore. Now I'm imagining this picture, but I don't care exactly about what this is. And max here, in principle, I take to infinity. Yeah. And yeah. So with this definition, the operator, so maybe let me mention the other symmetries. So the Hamiltonian commute with C symmetry, which is the thing that takes this configuration to this sort of configuration for length 3. So it flips the size of the Wilson lines. Okay, charge conjugation, and it commutes also with cyclic rotations by 1. Okay. And it also commutes with reflection, which takes, so in general, if you have 3 different operators, psi A, B, C of Z, it maps it to psi C, B, A of 1 minus Z. That also commutes with the Hamiltonian, and you have a cyclic rotation by 1. These 3 symmetries commute with each other, and you could diagonalize all of them simultaneously. And the eigenvalues of these guys are plus minus 1, and here it's a x over 2 pi I n or L. So roots of unity here. So general state with 3 things you will diagonalize. You could further reduce everything at 3 points to a single wave function, assuming all of these properties. Here we're looking at 3 identical fields. So in particular, this symmetry has to be equal to 1. Okay. And C can be plus minus 1, and R can be plus minus 1. R here for a symmetric operator basically tells you that the states with odd and even n don't mix with each other. We'll see this in Hamilton.
So you're like kind of describing how you're going to solve integral equation, right? Yeah. For eigenvalues. But yeah, can't you like do a couple of million transforms here, there, and like isn't it reducing to cubic third order differential equation if you?
Yeah, you could try to do smart things like this. Yeah, this is just to represent a rather dumb strategy. It's really not a unique strategy, but let me describe what it gives. So could you turn on the screen for the laptop, please?
Simon, is this R eigenvalue plus minus 1 related to spin parity or something like that?
Related to what?
Well, you have this symmetry, like when psi of z goes to psi of 1 minus z, and you can have plus minus 1 under it. Is it related to spin parity or not?
You mean a signature or?
Sorry?
Signature?
Signature, yeah.
Spin parity?
Signature, yeah.
For integer spin, it's minus 1 to the j. but
Okay,
in general,
okay.
I'm not sure. Yeah.
Well, I mean, in general, then it has to
in
be
general,
the
it's
same
still an integer. Yeah. Okay. Yeah. So just briefly describe this code. So this is the Hamiltonian written as there's a bunch of terms that are these things that you have to integrate over alpha, and so this is the simplest pairwise interaction between 1 and 2. But then when you look at the other pairwise interaction and map back the operator to this form, you get some factor like this. Like remember this 6th term in the Hamiltonian. You get something like this. There's some step function because you have to integrate. You have to remember to integrate when this operator move here. It can move all the way to the first one, so we can change the operator ordering. So you have to use the C eigenvalue at some places in the calculation when you cross when the ordering of the operators cross. So you can write the Hamiltonian that accounts for this effect. And it turns out that the action of this Hamiltonian on the monomial can be written explicitly in terms of these harmonic sums. I think it's generalized to non-integer n, but I haven't wrote it down. And then you can create explicitly these moments in terms of harmonic numbers. And then so basically that way you can quickly populate a matrix of this matrix A of HMN can be computed in terms of harmonic numbers. So you can populate this matrix rather fast. And here there's just a little technical trick. So I won't go to the code, but if you want to make, say, a 30 by 33 matrix, you have to calculate like 1,000 of these harmonic sums. But these harmonic sums, they all differ by integer. So you can be 1,000 times faster than Mathematica if you just evaluate one harmonic sum and use that. The difference in two harmonic sums is simple. So if you tabulate this thing beforehand, you get a much faster evaluation. And so this is a code that compute for a particular spin 2 plus 1/3. This is going to return all of the with a 10 by 10 matrix, precision 30, all of the states. So it's a bit quick. And there's something remarkable that I'm not so sure how to understand analytically. I think from integrability it's clear, but from spacetime it's not clear. If you put the C equal -1, so let's look at these numbers a little bit. If you put the C equal -1, so this second list of numbers is C equal -1, you get basically this exact same state. So the states, so the ground state is degenerate under C, and all the other states come in pairs. So you see that all the numbers in the first table, except the first, are in the second list. Okay? And there's a little bit of error here because I'm truncating to a lower order. But the error goes to 0. And you also see that here, because I'm using a small matrix size effectively, the lowest eigenvalues are pretty, usually the lowest eigenvalues are reliable, but the higher eigenvalue, they give you some complex junk. And this complex junk has to do with the fact that I'm using an approximation, a truncation that is not manifestly Hermitian. So I'm getting complex eigenvalues. But you're just supposed to throw away these high eigenvalues and focus on the low ones, which are very stable. So this code here computes it up to a basis size of 4t. And you can see roughly the convergence. So this is like the ground state, this first list here. You can see the ground state energy as a function of the size of the matrix. So with a 40 by 40 matrix, it gets, you see the numbers are very stable. And it's the same for all these other numbers. Okay. All right, so oops. Yeah. Yeah, you can see the convergence being achieved when the size of the basis long before it reaches 40. If you just plot the eigenvalue as a function of size of the basis, you get a plot like this, not very illuminating. One thing you can do is you can plot the residuals, so you can plot the error from the on the sign, and we just plot it. So one thing which is striking is that when you increase your basis size, I was shocked by this very simple-minded method. The error decays exponentially. And the number of useful states, because of this parity even odd, is basically half of this. So basically, every time you add one state, the error divides by 2. So it's a very rapidly convergent algorithm. So here you see that the first few states are converged to 10 to the minus 8 accuracy. Okay. And okay, by comparing with the integer spin solutions, you can also plot. You can also now the finally interesting to do is to scan over values of the spin. So we're going to go from -4 to 8, and unit of 0.1, and show you the eigenvalues for 30 by 30 matrix. It's going to take a few seconds. It's going to go up to 8. Sorry. Yeah. So this is the main result you find. So this is the spectrum you get from this particular numerical method. So on the horizontal axis is the spin of the operator. And in color, I've shown the local operators that you get. Okay. So the dot at the middle is the stress tensor multiplet, which is protected. Then this is the Konishi. And then you have these other guys. And at spin 6, the first time you have 2 operators. And if you keep going at higher spin, you get more and more of these local operators. One thing, I'm not sure if this was noticed in the previous work, there's kind of a trajectory in between the 2 first local operators. But it does come out of this problem. Yeah, so if you started from the local operator and try to
sorry, isn't this just this just the odd trajectory? Isn't this just the odd spin trajectory?
Ah. Yeah, you're right. Great. Yeah, right. There should almost certainly be a dot here at 3 on this figure and at 5 here. Thank you. Great. Yeah, so all of these trajectories have local operators on them. And you also see that as you go to spin -1, things diverge. You can see this rather explicitly from this matrix. Some matrix elements diverge. And the rank of what diverge is the 1 by 1 as rank 1. So you get a single state which go to infinity there. And yeah, I think when you go to the left of this, I'm not sure I trust the method, because this assumption that you have regular wave function may not be valid. So probably you should chop this plot at -1. And the last thing you can show is you can inspect the wave function, the eigenfunction, and see that they make sense. So this is the first few eigenfunctions. So you see that they're fairly smooth, and so here there's a sum of 30 polynomials, and you see that they are like fairly reasonable wave functions. But the latest one, they're just like they're not reliable wave functions. It's probably the first half or so which are really meaningful wave functions. The other one are truncation artifacts. Yeah.
What do you expect analytically for the behavior at z equals 0 and z equals 1?
Z equals 0 is very boring. Oh, sorry, z equals 0. Well, yeah, that's a great question. I think for integer spin, I don't really see, for positive spin, I don't really see a reason why anything singular should happen there. So, and that's supported by the numerics. The wave function, like they don't, like, let's put it like this. So, if the assumption that the eigenfunctions are regular at the endpoints was not correct, you will see the numerics trying to make crazy polynomials that blow up near the endpoints, because with like a polynomial of degree 30, it has the ability to create crazy polynomials which blow up at the endpoint. And I think the fact that it does not do that is evidence that the wave function is actually smooth. Okay, it's a reasonable assumption. Yeah.
So just to understand the plot, so you said, so this is for twist for
yeah,
3 scalars, right?
Yeah, this is for length 3.
But why did you say Kanishi is in there?
Sorry. Sorry, I said completely. Yeah, it's completely wrong. Sorry. Sorry, I think, okay, I should double check. I seem to remember that the lowest trajectory is a descendant of the twist 2 spectrum. But you have to double check this. I may be saying something completely wrong.
Then for length 3, I thought singularity should be at -2, not at -1.
That is, okay,
So
that would be
it's kind of
consistent with the
also
figure. Yeah, I
consistent,
should check where's the pole. Yeah, great. Yeah. Yeah, great. Yeah, and actually maybe anticipating tomorrow's lecture. So tomorrow I will compare this to the spectrum from QSC, but sorry, from QSC, but from the one loop Baxter function. But basically there will be agreement. It doesn't necessarily mean that this is the right answer, but I think it clarifies what you have to assume to get this answer.
But it should be covered by the Y system, right? It's a single trace separators in principle.
Yeah, exactly. Yeah. So also the quantum spectral curve should produce this. But my understanding is that the quantization condition that was used just for the SL2 one loop Hamiltonian by last year is essentially equivalent to the one you use in the quantum spectral curve, but I'm not entirely sure of the details. For non-integer spin, you have to use this. You have to allow some exponential behavior of some Q functions that they also have to allow. So we'll describe this assumption tomorrow, and maybe you can immediately say whether they're equivalent or not to what you do in the QSC. Yep.
You are done?
Yeah.
Basically, we have some more time. We'll stop.
How long do I have?
With questions, 1 hour 15. You have 5
Yeah.
more minutes, but we can stop here and go for
No, yeah, I think it's. I think it would be rushed if I tried to introduce the QQ equations, and it wouldn't do justice in 5-10 minutes.
But then maybe let me
Yeah.
again my question.
Yeah.
How do you think that? Do you have a way to argue that the function should be regular at z equals 0 and z equals 1? I somehow have a vague memory that it's not. Alexander, is it regular? Oh, it should be the same thing, no?
I mean, they're related by some map, but I don't think they're probably not the same. So there's some integral operator that's a pairing between this wave function and the thing you integrate against 3 operators. And you have to invert this pairing matrix to go from your wave function to this wave function. I think the assumption that this is polynomial is the assumption that this is regular at the endpoints, I think seems reasonable because we're looking at expectation value of product of 3 things. So it makes sense to have not this in a regular state. This eigenvalue should not need to diverge.
So just one comment about this, that I'm not sure if it works here, but say when we were doing a similar exercise in Nielsen-Fisher, one thing that you can do is you can look at this integral equation and then you can massage it, plug it into itself a few times, and then reduce it to some high-order differential equation. Once you have a differential equation, you can analyze the singularities, what kind of singularities you can have. And say in that case, we could say that, if the eigenvalue is, if the eigenvalue and spin satisfy this inequality, then it has to be regular because there are no singular solutions. But I'm not sure if you can do it here.
I think from the broader physical perspective, what the correct boundary condition is essentially determined by what kind of correlation function we consider to be physical, and what does the expectation value look like in these operators. So in the free theory, if you put, for example, some local operators here, and you compute this expectation value, it will satisfy this regularity condition that I described. So maybe you can cook up states where it's not satisfied, and then for these more singular states, you would have to look at a different spectral problem.
But just to comment, the actual wave function will have very singular. It will be very singular when particles collide, particularly in a mass reduced to delta functions, right? When you become normal operators.
Well, here this is taking care of.
Yeah, I think expectation value is proportional to delta function. You will need a very singular source to achieve that. So to having the expectation value of phi times phi have a delta function, you need a very singular source. So I agree. If you think about the operator which shows these things, delta functions are very natural. But in this dual problem of the expectation value, I don't think they are.
What happened to the blue light trajectory? Sorry, that one is still. But it disappeared at -2. And then
Yeah.
it's up there, and you don't see it.
Well, yeah, vague feeling is that it's kind of coming back and influencing all the other ones, but it's tilted the wrong way. So I mean, maybe you can see it coming back here, but you know, when it goes to -infinity is to go back up at +infinity. But I'm not sure I completely trust the spectrum to the left of here, because the assumption about regularity may no longer be valid when you. Here when you go to this negative j, you're really in this Hamiltonian, you're really pushing the dynamics closer to the endpoint.
So which of the trajectories is Q3 equals 0, 1?
Q equals 0 is the lowest one, yeah.
But that you said is descendant of.
Yeah, assume Q equals 0, I assume is a descendant.
But this is the trajectory probably with the conformal spin equal to 1. Your leading trajectory there, the blue one, is the one with conformal spin. So is it length 2 and conformal spin 1 or length 3?
Yeah, sorry, yeah, this is the thing at the middle as conformal spin 1. So yeah, it's dimension 3. It's a dimension 3 operator.
Yeah, so it's going to -1, and this is correct, because it's the trace of phi cube that is going to -2.
Yeah, exactly. So this is the half BPS operator of length 3. This is a trace of Z cube. Sorry,
yeah, because
it's not
otherwise
the
the first
substantial
operator
at
is
all,
the BPS trace of phi cube. In this case, is a trace of phi square with the conformal spin 1, I guess, no?
No, this is the axis is really spin. So the thing at the origin is really trace of Z cube.
Okay, so this is the singlet of the trajectory z derivative of s, derivative to the power s, z square, for example.
Exactly, and S is what I call J, yeah.
And this is just the singlet.
A cross singlet, but sorry, in terms of R charge, this is a symmetric. This is symmetric, traceless. This three index, 3 symmetric vector indices.
Okay, because for example, if the yellow one is the odd spin one, I'm expecting that there is more than one. Because for example, for s equal to 3, you have 2 solutions, not just one.
Okay. They're degenerate.
Yeah, no, but they are not degenerate. They are split apart of, you know, depending on G, obviously. If G is equal to 0, they are degenerate.
I can check. As you see, I botched my job and I didn't do the odd spin problem properly, but we can discuss it afterward.
Okay.
I can tell you if there's 1 or 2 odd spin and so on. I can tell you that, but not immediately. Yeah. Yeah. Maybe something else I can say. Yeah. If you put the spin here to be integer, something like, I don't know, not integer, but very negative, -2, -2/3, something like this. Then when you stare at the eigenfunction which come out, and you see really that I don't trust any of these wave functions, right? The spectrum kind of looks reasonable, but the wave functions are clearly telling you that I'm not in the correct basis of functions. So I don't actually trust these eigenfunctions to the left of this singularity. Exactly. It should be possible to NLT continue Hamiltonian, but you need to add more singular powers. Yeah, we have to analyze a little bit more what happens at the endpoints. So yeah. So this assumption of regularity, you see here I'm just showing is self-consistent of positive J, but for negative n of J, it's clearly not self-consistent anymore, and we should do something smarter.
Yeah, we understood with Alexandre and David how to go to the left now. We are writing it up. But typically what we see is that it's much better not to go really negative, but give a small imaginary part. If you go along the real axis, it's a mess.
Okay.
But if you go -3 plus I/4, it's much better.
Okay.
So if you go slightly above.
It's kind of an accumulation of branch points near the real axis.
Then you will need some real parts, yeah.
Maybe this is still not it. Okay.
Very good. Let's thank Simon.
Yeah.
So let's be back at 11:15.